Hi everyone, welcome to Modern Optimization Methods. Today we will take a look at the fourth part of Chapter 5, the rate of convergence. Now, let's recall that we are currently discussing the conjugate direction method, and we try to take a look at the convergence rate for conjugate gradient method when applied to quadratic optimization. Okay, so the first special case for a convergence rate of conjugate gradient method is as follows. If the matrix A has only R distinct eigenvalues, then the conjugate gradient method will terminate at most R iterations. Okay, so in other words, if you got a very special structure of coefficient matrix A, where this A has only R distinct eigenvalues, then our CG will terminate within at most R iterations. So it means that for different cases of coefficient matrix A, the performance of the CG method may different. Now let's take a look at the general case. For general case, let's first assume that the eigenvalues of the coefficient matrix A has a non-decreasing order, meaning that lambda n is the largest one and lambda 1 is the smallest. So we have the following convergence result. The distance between xk plus 1 to the accumulation point x star will be upper bounded by a constant which is related to lambda n minus k and lambda 1 multiplied by the distance of the original starting point to the accumulation point. Okay, so this is at the k plus 1 iteration we got the relationship. Okay, so in other words, at most, the convergence rate of CG method will be linear, or sometimes will be even faster than linear. It actually depends on the distribution of the eigenvalues in A. Let's discuss a very special case. Okay, so let's look at the figure here. We got some lambda 1 until lambda n minus m illustrated or clustered around 1, and for the other eigenvalues, they are far from 1. Okay, for lambda n minus m plus 1 until lambda n, they are actually far away from 1. In this case, actually the eigenvalues of A are grouped in two clusters. All right, so in this case, we can calculate that for lambda n minus m minus lambda 1, the distance between the two eigenvalues, they are actually very small, and which means that the coefficient here on the right hand side is much smaller. Therefore, you will get a very fast convergence rate. Okay? So for a small value of this epsilon, or the distance, we will get the very good performance of CG method, and CG will provide a good estimation of the solutions. So this is a general case for the convergence rate of CG method. Now we have another way to measure the convergence result, and recall that we define the condition number kappa A by the norm of matrix A multiplied by the norm of matrix A inverse, or in other words, the largest eigenvalue over the smallest eigenvalue. All right? Then, after defining the condition number, actually the convergence can be expressed in the following form. We got norm in terms of matrix A, okay? So the distance here is actually in the sense of A norm at the moment. then it will be upper bounded by a coefficient, which is actually a ratio, then multiplied by the initial point to the accumulation point, the distance. Okay? So as you can see that we got power k here. That means that as k grows bigger and bigger, you got shrinking optimal solution, meaning that the next iteration will even much closer to the accumulation point than the current one. And this actually demonstrates that the convergence rate of conjugate gradient method is actually very good when the condition number is close to 0. Okay? And as we mentioned before, that the CG method, the performance of CG method is actually closely related to the condition number. However, when the condition number is not good, the convergence rate may not that good. So we have to think about a way to improve the performance. Now, preconditioning is one way to improve the performance of CG method. So how do we do the preconditioning? So recall that we try to solve the linear equation ax equals b. If a got bad condition number, then we try to multiply a matrix before and on the right to the matrix A to try to improve the condition number. In other words, if we define a new vector x hat or new variable by cx, here C is a matrix, then accordingly we can get a new quadratic function with respect to x hat. Okay? And from this point of view, the original matrix A will transfer to a new matrix C inverse A C inverse. Okay? So this new matrix, we hope that it has a better condition number. Therefore, by design properly a matrix C, then we can improve the condition number of A. All right? And now the linear system gradient equals to 0 will become the new form here. So the new matrix multiplied by A hat, okay, the new linear system will equals to the right-hand side. So this is the preconditional version of CG method. In other words, we apply CG to solve this linear system, and then we try to get back to recover the vector A. So this is the idea of preconditioning CG method. Now, there are some advantages of the preconditioned CG method. One is that we can improve the current condition number of coefficient matrix A. The other one is that sometimes we try to choose a proper C. That C, you can choose it on your own, okay? So due to different situations, we can design different case of C to adjust different case of matrix A. So this is another way to improve the CG method. And sometimes for the matrix D or C, we do not need to worry about how we solve the C inverse, because in most cases, C is designed to be a diagonal matrix. So the inverse is actually easy to solve. All right? Now we present the preconditioned version of CG method, which is quite similar to the previous one. However, they are differs in some very small steps. For example, when we solve the initial starting point, we need to set, we solve my0 equals r0, this linear system. And here, this m is kind of the C inverse, all right? So it's the row similar to the C inverse. And after that, the extra part is here. When we calculate the step length alpha k, originally in the unpreconditioned case, this yk is actually the search direction pk or the current residual function r. Now, in the preconditioned version, we replace it by rk, okay? And xk plus 1 and rk plus 1 are the same as before. However, after we calculated the residual function, we need one extra step to get the original x. That is, we solve myk plus 1 equals the residual function to get yk, okay? Now, after that, the calculation in coefficient and the next conjugate direction, we all replace the original pk by yk plus 1, okay? So these are the difference from the unpreconditioned case. And after that, this will give us the preconditioned version of CG algorithms. And due to different applications, actually you can design different matrix M called preconditioner to adjust your matrix and improve the performance of CG. Okay? Of course, you may got many complicated implementation of preconditioner M, and this can be found in some very recent research papers, and we will not detail them here. Now, let's make a brief summary about this part. In this part, we mainly discuss the convergence rate of conjugate gradient method, and to improve further the performance result of CG, we also introduce the preconditioned version of CG method. Okay, so we stop here and see you next time.